All right, ladies and gentlemen, so there's just a couple of follow-up questions here at the end of the activity, so let's take a look at them. Number one just asks, how is utilizing molecular data, so things like amino acids, DNA, RNA sequences, how is that different from methods used to classify organisms and determine their evolutionary relationships? So think about how we use data at the beginning of the activity versus the type of data we used at the end. All right, so the point I want to kind of make here is just that it's different data. So when we look at molecular data, this is quantitative data. It's quantifiable, meaning that there's an ability to get um, direct numbers. So this data tends to be a little more difficult to obtain in the sense that I have to have the ability to access DNA or amino acids. I need to be able to have molecules from that organism, which, for example, if this is a fossil, isn't going to be possible. Um, and I also have to have access to the technology. So that can mean that some of these processes are a little more expensive, but it's a lot less subjective, meaning there's a definite number. If I have the data available, I can count it. And the number of differences that I find should be the same number of differences that anybody else who looks at the same set of data comes across. That being said, if I look at other types of data that we can use to determine these evolutionary relationships, things like physical characteristics, do they have hair, do they have feathers, or roles in their environment, so are they producers, consumers, that kind of thing. That data is a lot more qualitative, right? So they're qualities of an organism as opposed to actual numbers. And as a result, that does mean that that type of data is a little more subject to interpretation. What I may see as the organism playing this particular role in their environment, somebody may see a little differently. Um, and so some of that data can definitely be pretty cut and dry, and the vast majority of people would come to the same conclusion, but that's not always the case. So when we're creating these cladograms, the more data I can have across all platforms, the more I can be confident in the kind of relationships and patterns that I'm creating. So if I can couple both that physical characteristics, the roles in their environment, more of that qualitative data, and also have molecular data to back it up, and I get the same results, then I'm a lot more confident in the evolutionary relationships that I am hypothesizing. Okay, so let's take a look at number two. If the amino acid sequences between two species are similar, would you expect their DNA to be similar? Why or why not? So this continues to hit the same theme that we've been talking about over and over again, and this is stuff that we're going to continue to talk about this year, and that's just the idea of that flow of information in your cells, right? There is a connection between your DNA sets of instructions, the sequence of your DNA in your nucleus, to the amino acids, the proteins that we build, because that information is all related to each other. So if I find a difference in any one of those sequences, that does mean that there is likely a corresponding change to the other pieces of sequential information. So if I have a mutation that occurs in my DNA, it's going to cause changes to that RNA sequence and has the potential to cause changes to that amino acid sequence as well. All right, let's take a look at this one. So the idea of molecular clocks means that organisms that are more similar are closer together since they branched off from their ancestor. How might we use this idea? Again, the idea goes back to that sequential information, that DNA, that RNA, that amino acids. So the more similar their sequences are, which is really what these molecular clocks are talking about, the more recently they've diverged or branched off or evolved from each other, from that common ancestor that they share. The more differences that they have, the further back in time we have to go to find a common ancestor. As a result, that's why we put them further across a cladogram from each other. So the more sequences they have in common, the closer they are on that cladogram, which also means the more recently they have branched from that common ancestor. The more differences they have, the further apart on that cladogram they are from each other because we have to go further back in time to find the common ancestor that they share.